This is video 4C for the Year 12 Mathematical Methods course. In this video, we're going to cover the theory behind the fundamental theorem of calculus, under the topic of integration. Specifically, we are going to explore what is the fundamental theorem of calculus, how to use this theorem to calculate definite integrals, properties of definite integrals, working with non-positive functions, and then we're going to cover some example questions. A few chapters ago, when we first introduced the whole idea of integration and integral calculus, we discussed quite extensively how connected integration is to the area underneath a curve over a particular domain. In fact, that was actually what our entire first chapter was about when we were looking at the estimation method using upper and lower rectangles. And specifically, we were able to express the area bounded between a positive function in the x-axis over a particular domain by a definite integral. So just in case you need a bit of a reminder, we said that the area bounded between a positive function, we'll call this function f of x, and the x-axis over the domain of x being between a and b is given by the following definite integral. So the integral of f of x dx with a lower bound of a and an upper bound of b. And in fact, when we covered the first chapter all about the area underneath curves, we evaluated these integrals using our calculator to compare the true area underneath the curve to our over and under estimates. So just as a quick reminder as well, a visual representation of this could be something of the sorts, where we have a function like this, where this point here is a, this point here is b, and then this area underneath the curve here would be given by this integral expression over here. And as I mentioned before, what we focused on primarily in our first chapter was how we used the upper and lower rectangles in order to estimate this total area, because we found that in certain situations we could find the exact area very easily using some very basic geometry, for example constant and linear functions. However, as soon as we got into functions such as quadratics or cubics or surds or anything that involves a curve, then we couldn't use basic geometry to find the exact area, so we had to rely on the method of estimating using upper and lower rectangles. However, what we're going to be focusing on in this video is how we can use anti-differentiation to help us find the exact area underneath curves. So the focus of today's video is how we can use anti-differentiation to find the exact area underneath curves. And in order to do this, we're going to introduce quite possibly one of the most important theorems you're going to have to learn in regards to calculus as a whole, and this is called the fundamental theorem of calculus. And as you can imagine, the fundamental theorem of calculus essentially underlines a lot of what we're going to be doing from here on out. It's how we essentially link together differential calculus with integral calculus, and then overall link that to finding the area underneath curves between a particular domain. So before we introduce the fundamental theorem of calculus, we will have to just do a quick bit of recollection from our previous video all about anti-differentiation. So if you quickly recall from our last video, we said that if f of x, capital F of x that is the antiderivative of f of x, then these two functions are connected by the following relationship, where capital F dash of x is equal to lowercase f of x. So we spent quite a bit of time in the previous chapter going through this whole idea of antiderivatives and how to find the antiderivatives of different functions using calculus. And the good thing about this chapter then is that we're going to be using a lot of those same techniques to find the antiderivative, but then we're just going to be taking it an extra step further. So what the fundamental theorem of calculus then tells us is that if we have the integral from a to b of our function lowercase f of x dx, then this here is going to be equal to the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. Now, I cannot stress this enough. This theorem here is going to be one of the most important things you will learn in this entire topic of integration. So that is why we're going to be going through this quite a bit right now, and why we're going to be practicing this heaps. Because knowing how to actually evaluate integrals between an upper and lower bound using antiderivatives is essentially what we're then going to be basing the rest of this chapter on. But now, if you prefer to write this in a sentence form, then we can say it like this. The definite integral from a to b of the function f of x is given by the antiderivative capital F of x evaluated at the upper bound b minus the antiderivative evaluated at the lower bound a. So then, as you could imagine, if we're just being asked to evaluate a definite integral between an upper and a lower bound, then all you need to do is find the antiderivative of the function using the exact same process that we covered in the last video, and then evaluate it at each bound, and then just subtract the answers. So it's a very, very natural continuation of what we just did, and honestly, if you're feeling pretty confident now in how to actually find the antiderivatives of functions using differentiation, then this stuff here should be an absolute breeze in the park, because it's just a simple substitution and then a subtraction. Now, from this, before we actually start getting into some questions, we do have some important rules that we need to go through when it comes to definite integrals. The first one, and we can actually show this geometrically as well, is that if you have a definite integral of a function f of x dx, and you evaluate this with this same upper and lower bound, in other words, the upper and lower bound are the exact same value, then this here will automatically be equal to 0. Now let's actually quickly go about showing this geometrically. So if you could imagine, let's say we've got a function f of x, we've got this boundary here which is a, then we know that this integral here will be the area underneath the curve from a to a. However, if you just go from a to a, then essentially what we're creating is a straight line. And a straight line does not have any area, therefore the entire integral must be equal to 0. So that's our first important rule there. The second one is that if you have a definite integral from a to b of a function f of x dx, then if you swap around the boundary points, then you can absolutely do this. So now we're going to go from b to a of f of x dx, but we need to put a minus sign out the front here. So you could almost think about this similar to inversing the integral sign, but you've just got to make sure that you pop a minus out the front there as well. The third rule, and this one again can be shown geometrically, so we'll absolutely do that, is that if you have a integral from a to b of f of x dx, and then you add on another integral, where the lower bound of this one is going to be the same as the upper bound of the previous integral, and then a different upper bound of the same function, f of x dx, then this can combine into one overall integral with a lower bound of the first integral, so a in this case, and an upper bound of the second integral, c, of the exact same function. Now, similar to before, let's actually go about showing why this is. So let's say we have the function f of x, and that's something like that. Let's say this point here is a, this point here is b, and this point here is c. Then what this red area here would indicate is this integral here, because it's the area bounded between a and b. This green area here would represent this second integral, because it's the area bounded between b and c. And then the overall thing, which I'm now going to color in blue, is going to be the integral from a to c, so this one here. So we can clearly see then that the red area plus the green area will be equal to the entire blue area. So in other words, this first integral plus the second integral must be equal to the third integral. Then the next rule, if you have an integral from a to b of two functions either being added or subtracted together, so you can say f of x plus or minus another function g of x dx, then you can split this integral up into two separate integrals of one for each of the different functions. So we're going to have one integral of a to b of the first function f of x dx, and then whether it's a plus or a minus, you'll keep that consistent, but then you'll open up a second integral between the same boundaries a and b of the second function g of x. And then the next rule here is what happens when you have a constant out the front of a function. So in other words, if you have the integral of k, a constant, multiplied by a function f of x between the bounds of a and b, well, very similar to our rules of differentiation, if you have a constant inside of the integration sign, then we can just pull that out to the front of the integral. So this can be rewritten as k, the constant, pulled out to the front, and then the integral just as it normally would appear. So again, you can think about this rule here being very, very similar to our differentiation rules. So you've got a bit of symmetry there between the two. Now, the last thing here that I really, really want to cover before we actually go into the process of evaluating definite integrals is what happens when a function is not always positive. Because across the first chapter where we dealt with approximations using upper and lower rectangles, and even at the start of this chapter here, we very, very clearly defined that our function f of x needed to be a positive function. In other words, if we had a function with this particular graph here, and we were considering between the boundaries of a and b, then essentially the main requirement was that every single point of the curve between these two boundary points needed to lie above the x-axis, and we couldn't even begin to consider what would happen if it was below the x-axis. In fact, all the examples that you've gone through over these last few chapters, you'll notice that every single function is always lying completely above the x-axis, but now we're going to consider what happens if you have a situation potentially like this. Let's say we had a sine wave, we had some above, some below, and then again, some above. And just for simplicity, I'm going to set up the lower bound of our consideration to be this point here, A, and the upper bound to be this point here, which is B. Now, just as a little bit of notation, I'm going to call this green area here A1, this area down here A2, and this area here A3. Now, this is the very, very important rule. Let's say you had a particular boundary, let's call it alpha and beta, just to mix things up a little bit. If your function, f of x, is less than 0 inside of this boundary, then the integral from the lower bound to the upper bound of your function f of x dx will be equal to the negative version of whatever the area is bounded between the x-axis and that curve. So this relationship here is once again a very, very important one, because it means that we can't always treat a positive and a negative function to be the exact same when it comes to integration. So linking this to this graph here, what that means is, let's say I define this point here as x1 and this point here as x2, just choosing some random variables here, then it means that the integral from a up to x1, so this part here of f of x dx, will be equal to the area a1. So that's going to be no problem there because the function is positive, so we know that it will just equal to the area. If we now consider the integral from x1 up to x2, so that's this section here, then the integral of f of x dx will be equal to the negative version of a2, because in that entire region there, the function lies below the x-axis. And then finally, if I consider the integral from x2 up to b, so in other words, this section here of f of x dx, then because the function once again is entirely above the x-axis, then we know that the answer for this one will be that third area. So the reason why this is very, very important is because in certain situations, you will be asked to find the total area enclosed between two boundary points. If we consider this example here, they may ask you to find the total area enclosed between points A and B. In other words, to find the three black shaded areas which I've just done there. In which case, if you were asked to do that, then the total enclosed area would not be equal to the integral from a to b of the function f of x. The reason being is because whilst this section here and this section here are positive, so you'll get the right areas, this middle section will be negative, so it means that your overall integral will actually be less than the true area. So the way that you would tackle this one here is you would do the total area is equal to the first integral from a up to x1 of f of x dx, and then we will subtract away the integral for the second section, so that's the integral from x1 up to x2 of f of x dx. And then finally, we'll just add the last integral, which will be from x3 up to b of f of x dx. Now, the reasoning for this is because of the following. We've said that this integral here is equal to a1, so I can just replace this first integral with a1. Then we're going to minus this second integral, which we've said is equal to negative a2, so I'll pop negative a2 there. And then this last integral is equal to a3, so I'll pop a3 there. So then if we simplify this, we get a1 plus a2 plus a3. So essentially the rule is, if you want to find the total area enclosed in these different sections where a part of a function lies below the x-axis, then it means that you'll then have to subtract away the integral which reflects the area bounded between the 2 points where the function lies below the x-axis. Now this will become quite important as time goes on, but definitely try and look at this sooner rather than later and get a good understanding as to the correlation between these positive and negative integrals when the function lies above and below the x-axis, and it means that the rest of this will come out to be a little bit easier. However, one thing I'm definitely going to suggest is memorizing this relationship here, which essentially just describes everything that we talked about, and then actually try a few questions which have functions where sections of it lie below the x-axis, and make sure you understand how you can break up the integrals appropriately to make sure you get that nice final answer. Alrighty. So now that we've covered that, let's go through a nice process as to how we can use anti-differentiation to evaluate definite integrals. So, step number 1, and I'm not going to detail all the same steps that we went through in the previous video because hopefully you would have had quite a bit of practice at that by now, but we are going to use the process of anti-differentiation to find the antiderivative of the function you are finding the area for. And the steps for this are in our previous video 4b, so if you need a bit of a refresher, I would highly recommend you go back to that video and make sure you understand how to do that. Once you have that antiderivative, you're going to evaluate the antiderivative at the upper and lower bounds of your area. And subtract the lower bound result from the upper bound result. And then a step very, very similar to what we did in our approximation using rectangles chapter, we are going to use the integral function on our calculator to confirm your result. You guys know at this point that I'm a very big fan of using your calculators to make sure that any result that you get on a test or exam or even just generic questions is correct. And because of how easy it is to do integrals on your calculator, you may as well make sure that you're doing the right thing whenever you're doing a question regarding definite integrals. And then fourth and final step, if the function is positive in the given boundary, then the integral will be the area bounded between the function and the x-axis. So the important thing about this last step here is that once again, because of everything that we just discussed about when a function is positive and negative, the integrals that we calculate using anti-differentiation will only represent the area bounded between the function and the x-axis if the function itself is purely positive. And because of the fact that a lot of these questions will be asking you to find some form of area, very similar to what we did in our questions related to the over and under estimates of the area using the upper and lower rectangles, we need to make sure that we always give our answer in the form of the number and then units squared. So remember, whenever you're talking about some form of measurement, it doesn't matter whether it's length, area, volume, whatever, you need to make sure that your answer always has some form of units associated with it. If you do not include those units, then you'll be absolutely deducted some marks in a test or exam. Now, with that being said, let's get on with some example questions. Example A. By differentiating x squared, find the exact area bounded between the x-axis and the function f of x is equal to 2x for x being bounded between 10 and 5. Alrighty, first thing we're going to do here is come over to our graphics calculator and indeed confirm that this function here is entirely positive between 5 and 10. So if we come to our graphing mode, we're going to plot out the function of 2x, and if we set the boundaries being between 5 and 10, then we can clearly see that the entire graph is above the x-axis, so we know that that check there is done. So we can therefore say that the exact area will be given by the integral from 5 to 10 of the function f of x, which is 2x dx. So what we need to do is find the antiderivative of 2x. And we're being told to first of all differentiate x squared. So we know that the derivative d by dx of x squared is equal to 2x. So because we've got a differential equation in this format here, then what this here means is that the antiderivative of 2x is equal to x squared. So then if we want to calculate the area, then we therefore know that we're going to evaluate the antiderivative at the upper bound. So that will be equal to 10 squared. Then we're going to subtract the antiderivative evaluated at the lower bound. So then that will be 5 squared. 10 squared is 100, 5 squared is 25. So then we get an exact area of 75 units squared. And let's quickly double check to make sure this answer is correct by coming over to our graphics calculator and evaluating this integral through here. So if we go options, calc, and the integral, we've got the integral of 2x, and we're considering this between 5 and 10. Evaluating this, we get an answer of 75, so we know that we're pretty good from here. So now, example B, by differentiating x cubed, find the exact area bounded between the x-axis and f of x equals x squared, for x being between 0 and positive 3. So the first thing that we can do here is come over to our graphics calculator into the graphing mode and make sure that our function of f of x equals x squared is entirely positive between 0 and 3. So if we pop in x squared, and we're going to set the boundary being between 0 and 3, then we can clearly see that the entire graph is above the x-axis, so we know that we're all good here. So because of this, we know that the area is going to be given by the definite integral from the lower to the upper bound, so from 0 up to 3, of our function x squared dx. So in order to evaluate this definite integral, we first of all need to find the antiderivative of x squared. And we're being told in the question to first of all differentiate x cubed, so let's do that. So we know that d by dx of x cubed is equal to 3x squared, but I want to try and get this x squared all by itself, so let's divide through both sides by 3. We get 1 over 3 d by dx of x cubed is equal to x squared, and then if I pull in this constant of 1 over 3 into the derivative, I get the following equation. D by dx of 1 over 3 x cubed is equal to x squared. So then from this equation here, I can therefore say that the antiderivative of x squared is equal to this function here, which is 1/3 of x cubed. So therefore, I know that the area will be equal to this antiderivative evaluated at the upper bound, take the antiderivative evaluated at the lower bound. So that will be 1/3 of 3 cubed, take 1/3 of 0 cubed. 1/3 of 3 cubed is going to be equal to 9, then 1/3 of 0 cubed is equal to 0, so then we get a final answer of 9 units squared. And what we can do here is quickly evaluate this integral expression in our calculator to make sure that we get the same answer. So if we come over to our graphics calculator, go back into run matrix mode, then you can go options, calc, the integral. The integral in this case is for x squared being between 0 and 3, and we get an answer of 9, which is the exact same answer that we got here. So we know that this answer must be pretty good as well. Example C, by differentiating e to the power of 2x, find the exact area bounded between the x-axis, and f of x is equal to e to the power of 2x, for x being between ln3 and ln4. So the first thing we're going to do is come over to our graphics calculator in the graphing mode. We're going to pop in our function, which is the e to the power of 2x. We're going to evaluate this between our upper and lower boundaries, which is ln3 and ln4. And we're going to make sure that the entire function is positive, and we can clearly see here that the entire function in this boundary lies above the x-axis, so we therefore know that the area is going to be given from the integral from the lower bound to ln3 to the upper bound to ln4 of the function e to the power of 2x dx. So in order to evaluate this definite integral, we first of all need to find the antiderivative of e to the power of 2x. Now the question first of all asks us to differentiate e to the power of 2x, so let's do that. So d by dx of e to the power of 2x is equal to 2 multiplied by e to the power of 2x. Now I want to get this e to the power of 2x by itself, because that's what we're trying to find the antiderivative for. So I can first of all divide both sides by 2, in which case I get 1/2 of d by dx e to the power of 2x is equal to e to the power of 2x. And then I'm going to pull this constant of 1/2 into the derivative sign, which then leaves me with d by dx of 1/2 e to the power of 2x is equal to e to the power of 2x. So what this differential equation here tells us is that the antiderivative of e to the power of 2x is this inner function here, which is 1/2 e to the power of 2x. So now that we have that antiderivative, we therefore know that this integral up here is going to be given by the antiderivative evaluated at the upper bound, take the antiderivative evaluated at the lower bound. So therefore, the area will be equal to the antiderivative evaluated at the upper bound, which is going to be 1/2 e to the power of 2 ln4, take 1/2 e to the power of 2 ln3, which is the lower bound. And just as a bit of practice with our exponentials and logs, let's evaluate this by hand. So with this first term here, we can write that as 1/2 e, and then the 2 ln4 can be rewritten as ln4 to the power of 2 by bringing that 2 up as the power. And then this second term we can rewrite as 1/2 e, and then ln of 3 to the power of 2, because we can bring that 2 up as the power. In which case we get 1/2 e to the power of ln of 16, take 1/2 e to the power of ln of 9. And then this first term here, the 1/2 e to the power of ln 16 will just be equal to 1/2 of 16, and then the second one will be 1/2 of 9. In which case we're going to get 8 minus 9 over 2, which is equal to 3.5 units squared. And just as a quick final check, let's come back up to our integral expression up here, pop this into our calculator to make sure that we get the exact same answer. So if we go into our run matrix mode, options, calc, integral, and we've got the function e to the power of 2x, and we're evaluating this between ln of 3 and ln of 4, and we can see that we get an answer of 7 over 2, or in other words, 3.5. So we can therefore say that this answer here must be correct. Alrighty, let's wrap up. So in this video, we revised how the area under the curve of a positive function over the domain of x being between a and b is given by the integral of f of x from b to a. We then introduced the fundamental theorem of calculus, which states that if the antiderivative of the function lowercase f of x is capital F of x, then the integral of lowercase f of x from b to a is equal to capital F of b minus capital F of a. We discussed how this theorem can be used to therefore calculate the exact areas under curves without the need for estimation. Some properties of definite integrals include the integral of f of x from a to a is equal to 0. The integral of f of x from b to a is equal to the negative of the integral of f of x from a to b. The integral of f of x from b to a plus the integral of f of x from c to b is equal to the integral of f of x from c to a. The integral of f of x plus minus g of x from b to a is equal to the integral of f of x from b to a plus minus the integral of g of x from b to a. And then finally, the integral of k multiplied by f of x from b to a is equal to k multiplied by the integral of f of x from b to a, where k is a constant. For a function f of x, which is negative over the domain of alpha to beta, then the integral of f of x from beta to alpha is equal to the negative value of the area captured between the curve and the x-axis over that domain. Finally, we outlined a process to solve definite integrals and therefore the exact area underneath curves using anti-differentiation, which was then applied to some exam-style questions. And that's it for now. See you in the next video.